Okay, so just to, so I'm going to continue with the material of chapter 1, which is mostly a review of stuff that I think you have seen before with maybe a couple of extra ingredients added on. So we were talking about Lie derivatives, so let me just go back to that for just a second. And what we saw was that this is a way of constructing derivatives of vectors and tensors in such a way that you don't need to introduce a connection. Therefore, you don't need to introduce an additional structure on your manifold. This is something that's purely intrinsic to a differential manifold, doesn't require extra ingredients. And in physics, it has this very important property that it's really the notion of derivative that tells you how to express the notion of invariance of a tensor field under a translation in some particular direction in space-time. So that's something that we talked about last time. So just to recap a little bit, when we take the Lie derivative of a vector A in the direction of u, the operation is that first you take the derivative of A in the direction of u, and then from that you subtract the derivative of u in the direction of A. And the statement here is that even though individually those terms are not tensorial, you cannot, so partial differentiation is not a valid tensorial operation. Individually, you're not dealing with the tensor here, you're not dealing with the tensor here, but with the minus sign and with this particular combination, the claim is that the operation is tensorial. So the thing on the right-hand side would actually transform as a tensor under a coordinate transformation. And that's something you can check explicitly, or you can just understand that this has to be true because the way that we define this geometrically, remember the diagram that we drew last time, the way that we define the operation of Lie differentiation on vectors is something that was defined in a proper tensorial way. So if the left-hand side is tensorial, well, it has to be true that the right-hand side is tensorial, but that's something you can always check independently. One way of checking this is to verify that, in fact, you could, if you wanted to, rewrite everything in terms of covariant derivatives. And that's another way of writing down what the Lie derivative is. But now, of course, it sort of obscures the point that I was trying to make before, which was the Lie derivative is a primitive operation that doesn't require a connection. If you express it in terms of covariant derivative, well, you bring in the connection, so it sort of, it obscures that point. But that's not terribly important. The point, of course, is that the connection terms that you bring in by taking a covariant derivative instead of the partial derivative actually cancel out in that equation. So if you were to expand out the covariant derivative here and here, you would find, because of that minus sign, that the Christoffel symbol terms would actually drop out, and you would get back to this expression over here. So obviously, though, this is a tensorial operation because each term individually is a tensor, and then you can verify that the Christoffel symbol terms drop out, and you end back to that expression over here. And again, that shows that even though individually you're not dealing with the tensor here and here, the combination is actually tensorial. All right, so that's the Lie derivative of a vector. We can take the Lie derivative of a dual vector, and that's something that's almost the same construction, except that instead, so now we take the derivative of p in the direction of A, but we add the derivative of, the derivative of A I always mess up the indices. Sorry, there's no A. There's a U. So now we add the derivative of U in the direction of P. So that's how it goes. So it's not quite the derivative of U in the direction of P. I'm actually differentiating U and then multiplying by P. That's how the indices work. And this is, again, something that can be written in terms of covariant derivatives. And again, you find that Christoffel symbol terms will cancel out in that combination because when you expand out the covariant derivatives, you pick up a plus sign from here, but you pick up, sorry, you pick up a minus sign here, you pick up a plus sign there, and the terms just cancel out. And then you can keep going like this, so the operation can be defined on, say, a tensor. And again, you would take the tensor and you differentiate in the direction of u. You would then add two terms. We add terms when the indices are all down. So the first term we would add is where we take u beta, differentiate in the direction of gamma, and sorry, I should write it in the following form. So, so I'll call it mu, and then we differentiate in the direction of gamma, and we multiply by the tensor, and then we add an extra term where we now differentiate. Am I going to mess this up? No, perfect. I'm sorry about that. My brain is taking some time to boot up this morning. So we do this, and then we have that. So that's the Lie derivative of a tensor, and then you have all sorts of possible combinations depending on the placement of indices and how many indices you have. And this is also something that can be written in terms of covariant derivatives. And the story is always the same. You always find that all the Christoffel symbol terms that appear when you expand out the covariant derivatives just cancel out, and you end up with the first expression. Okay, so that's the notion of a Lie derivative. And the continuation of that story then is when we start talking about killing vectors. And the last thing I should say is that if in some coordinate system the tensor A alpha beta is independent of some coordinate x naught, then the way to say this, so the way to say this in terms of coordinates would be to say that the partial derivative of the tensor with respect to x naught would be 0. But what I want to say is something more covariant. The way to say it covariantly is to say that in that case, the Lie derivative of that tensor field is 0 when the vector field is aligned with the coordinate lines where x naught is running. So the vector field in that case would be identified with the direction along which x naught is running, and all the other coordinates are constant. So this is the way of expressing covariantly the property that a tensor field of some sort is invariant as you make a translation along a certain direction in space-time. So here the direction was selected to be the direction along which x naught is increasing, but all the other coordinates are kept constant. But I can choose, I can choose to describe a direction in terms of a vector field instead of coordinate lines. And if my vector field is invariant under translation along u, then the way to express this is to say that its Lie derivative is 0. So this is really invariance of the tensor in the direction of the vector u. And that notion turns out to be very important, because if you have a symmetry in your space-time, for example, if vectors don't depend on time, or if vectors don't depend on rotation along some axis, then the way to express this, in a covariant way, is to say that the Lie derivative of that tensor is going to be 0 along the appropriate direction, either a time translation or a rotation along an axis. So the way to express this is to use the Lie derivative, and the vector along which you have the symmetry then becomes what's known as a killing tensor. Killing was actually, a person, some mathematician who formulated all of this. So a killing vector, more specifically, is it's a vector field and usually it's denoted with the letter C, such that the Lie derivative of the metric along C is 0. So that's the definition of a killing tensor, and killing vector. And what it means is that we have a symmetry of the metric along the direction along which C points. So if we have a metric that doesn't depend on time, we can say that, well, the partial derivative of the metric with respect to the time coordinate vanishes. But a better way of saying this geometrically is to say that we have a vector field that points along the time direction, and we have a metric that's Lie differentiated, whose Lie derivative in that direction vanishes. So it could be a symmetry with respect to time translations. That's pretty common. That could be, if the spacetime is axisymmetric, it could be a symmetry around, along a rotation, in which case the vector would be pointing along, the phi direction. It would be, the generator of the rotation. Or we could have, for example, in cosmology, we would have symmetries for spatial translations, in which case the x, y, and z directions would be symmetry directions. We would have a killing field, killing vector field in all three directions. And then there are more exotic types of symmetry. And for four-dimensional spacetime, in fact, the largest number of symmetries you can have is 10. And de Sitter space is an example of a spacetime that has all 10 symmetries. So you have the 4 symmetries associated with moving in any particular direction. You have additional symmetries associated with rotations and boosts. You can boost yourself in de Sitter space and don't see the difference. And if you count them, you have 4 translations. You have 3 rotations. You have 3 boosts. So I think that adds up to 10. I'll do the math later. And that's the maximum number of symmetries you can get. And examples of maximally symmetric spacetimes like this, well, you have basically Minkowski that satisfies all of this, and de Sitter spacetime that satisfies all of that, and that's it, anti-de Sitter space also. So this concept of a killing vector field is very important. It's really the statement that we have a symmetry in our problem. And depending on applications, you may have all the way up to 10 killing vectors to play with. Typically, you have much fewer than that. If you're dealing with spherically symmetric spacetimes, you have 3 to characterize the symmetry on the rotations. If you have a static and spherically symmetric spacetime like a Schwarzschild, well, then you have 1 more. You have the time independent symmetry, so you have 4. So 4 in practice is about as much as you can deal with in typical situations. So that condition translates into an explicit condition for the vector field itself. So if we plug that into the definition of what the Lie derivative stands for, well, what we find is that 0 has to be equal to the covariant derivative of the metric in the direction of C. And then we have 2 other terms. We have the derivative of C, and then we multiply this by G. And then we have another derivative of C, and we multiply that by G again. And that can be simplified because the covariant derivative of the metric is always 0. That's a property of our connection. It's a metric compatible connection, so that guarantees that the covariant derivative of the metric is always 0. Because the covariant derivative of the metric is always 0, the operation of covariant differentiation and multiplication by the metric commute. So I can rewrite the second term as G mu beta multiplying C, all covariantly differentiated with respect to alpha. And that's fine because, again, the partial derivative of the metric commutes. The covariant derivative of the metric commutes. I can do the same thing with the second term. And what I get out of this is the statement that after lowering the indices on the vector, I find that the covariant derivative of the killing vector has to satisfy this property, which says that the covariant derivative of the killing vector field has to be an antisymmetric tensor. So the symmetric part of the tensor vanishes. So one way to search for symmetries, if you're given a metric and it doesn't look like it has any, or that no symmetry is really forthcoming when you stare at the metric, is to set this up as a system of partial equations, and you try to find as many solutions as you can. And if you're a good mathematician, well, you know how to do that, and you can find solutions. And if you have solutions, that means you have a symmetry for each solution you find, provided that they're independent solutions. So sometimes you're presented the metric in a very strange coordinate system that doesn't particularly reflect the symmetries of the space-time itself. And when that's the case, well, you have to go and hunt for symmetries if you suspect that they're there. And a systematic way to do that is to try to integrate those equations and find solutions. Usually, or sometimes, or in the best of situations, you would set up a coordinate system that would, from the start, reflect the symmetries of the problem in such a way that the existence of killing vectors would be obvious by staring at the metric. So just a quick example of this: if you're given a static spherically symmetric space-time, e.g. Schwarzschild, then the metric would be of this form. And F for Schwarzschild would be given by 1 minus 2m over r. And two things you notice right away by just looking at the metric is the fact that there's no dependence on time, and there's no dependence on phi. So already we know that we have two killing fields, two obvious killing vectors. One would be the one that's aligned along the time direction. So in components, there would be an entry along time, so that's t r theta phi. So that's the vector that's pointing along the time direction. And then there's another killing vector that points in the direction of phi. That's the killing vector that tells us that we have an invariance along a rotation along the z-axis. Those are the two obvious killing vectors because you see right away that there's no dependence on phi and there's no dependence on t. What you don't see right away from the metric is the fact that, in fact, we have more symmetries than this. We have more than just an axial symmetry around an axis. We have full spherical symmetry, so that there are two other killing vectors that you don't see right away that that don't correspond to an invariance along a particular coordinate. And that's something that, in order to find and identify, you have to work a little bit harder. One way to do it is to remember that, well, this is all related to angular momentum, so that the killing fields, in fact, turn out to be related to the angular momentum operators in quantum mechanics. Another way, though, to find the other killing vectors that are missing here is to go back to the system of equations and try to find them that way, find other solutions to Killing's equation from the ones that I displayed here. So I won't go through the details of that, but in the book I actually write them out for you, and you can verify for yourself if you wish that they're really solutions to Killing's equation. But basically the point is that this reflects the time translational invariance. This only reflects the fact that you have an axial symmetry. You can rotate this way. What we're missing here are the killing vectors that tell us that we can in fact rotate in arbitrary directions, so that we have, for full spherical symmetry, we need to have 3 killing vectors because there are 3 directions around which we can do rotations. All right. Clearly, none of this depends on the identity of the metric function here or here. So I'm just taking Schwarzschild as an example. But if I had any static and spherically symmetric spacetime, that would also be the case, that those 2 vectors are killing vectors. Now, one very useful thing about killing vectors is the fact that they give rise to conserved quantities. So that's always a connection that we find. So that goes back to Lagrangian mechanics. Whenever you have a system that has a symmetry in it, there's always a conserved momentum. So momentum conservation always reflects the symmetry of the dynamics. Here, what we can do is to use the killing vectors as a way of displaying a connection between, again, a symmetry reflected by the, described by the killing vector, and a constant of the motion if you have a particle following a geodesic in that spacetime. So that turns out to be a very useful thing to have. If you have a killing vector, you can identify constants of the motion when your body moves on a geodesic. So killing vectors can be used to construct constant of geodesic motion. And it's important here that we're talking about geodesic motion. If if there was a force acting on a particle preventing it from moving on a geodesic in space-time, then then even the existence of a killing vector could not guarantee that you have a conserved quantity. In order to do that, the external force would also have to satisfy the symmetry, and that's by no means guaranteed. So there are certainly situations where it does happen. An example would be where, for example, there's an electromagnetic field in the space-time that also satisfies the symmetries of the space-time, time translational invariance, for example, or axial symmetry. So in those situations, when both the external field and the metric satisfy the killing symmetry, then you can still find conserved quantities. But you really need to have all of that, right? So if you have a symmetry in the metric, but no symmetry in the applied external field, then there's no constant of the motion. So right now, I'll just consider the case of geodesic motion. In one of the homework problems I'll give you probably next week, or even maybe this afternoon, I'll give you a problem where you have a particle with a charge interacting with an external field, and you're going to see that, well, if you have a killing symmetry in the external field, you will get a constant of the motion, which is the typical electromagnetic momentum that has mv in it, but also a term involving the vector potential for the E and M field. Okay, so the way this works is that we're going to assume that we have a geodesic that is finely parameterized, and that's also important. And for my purposes here, I'll just take the affine parameter to be proper time. That would be the usual one the one we take. So that means two things. We have a velocity vector u that satisfies the geodesic equation in affine parameter form, which means that the covariant derivative of u along u is 0. If we didn't have an affine parameter, we would get the kappa u term that we saw last time, but I'm not considering that case over here. We have that, and let's see, do I need this here? No, that's all I need, okay. A consequence of this that I don't need, but I'll just write it anyway, is that whenever you have a vector field that satisfies this, you have the consequence that the inner product, the norm of the vector field happens to be a constant. So that you can show is a direct consequence of the geodesic equation if you have an affine parameterization. So that's very simple. It just follows from that. You just differentiate this and find that the result has to be 0 by virtue of that equation. Okay, but that turns out that I don't need this property for proving that we have a constant of the motion if we have a killing vector. So what's the constant of the motion? Well, I want to prove that this combination here, the inner product between the velocity vector and the killing vector, is a constant. So of course, to prove this, I need to prove that the derivative of this with respect to proper time is going to be 0 as I follow the particle in its motion. So what we want to prove is that the derivative of the scalar quantity with respect to proper time is 0. So I'm going to calculate this and show that it's 0. And in order to do that, I have to use the product rule and differentiate each term separately. Because I'm dealing with a scalar here, there's no distinction between covariant derivative and partial derivative, so I'm just going to rewrite this as a covariant derivative of a scalar quantity. But in this form, I can say that I can use the product rule and say that the covariant derivative of a product is going to be the covariant derivative of each term added together. So that's going to be equal to the covariant derivative of u with respect to tau. And then we're going to have the derivative of xi with respect to tau. Well, the first term is easy. That's 0 by virtue of the geodesic equation. That's the same thing that I wrote down up here. The next term, what I'm going to do is to just write it in full. It's going to be u alpha that multiplies the covariant derivative of xi in the direction of u. And just to rewrite this slightly, I'll just write it as the product of the covariant derivative of xi that multiplies u alpha multiplies u beta. Here I could display a couple of more lines to show that this is 0, but I'll just use something that's a very convenient trick. Whenever you have a tensor that's antisymmetric, which we know it is because it's a Killing vector, multiplying another tensor that's symmetric, automatically the result is 0. And if you doubt that, or if you don't see that right away, you can prove it for yourself in about a line or two. It's a very simple thing, but it always works. So whenever you have a symmetric tensor that multiplies an antisymmetric tensor, the result is always 0, guaranteed. And that's very good to keep in mind. It's very good to remember that rule because when you do a long calculation, you can spot all sorts of terms that vanish because of the symmetry property. So that's something that's often very useful when you play with the Riemann tensor, when you end up dealing with a very long computation involving the Riemann tensor, because of the various symmetry properties of the Riemann tensor, especially its antisymmetry property under all sorts of exchange of indices. We'll come to that in a few minutes. But you can spot terms involving the Riemann tensor that would multiply symmetric combinations, and you can just drop them. They're 0 automatically because of that feature, and you don't have to worry about them anymore. So you can really cut down the size of a calculation a lot by remembering that quick rule. So just to summarize, this is antisymmetric. This is symmetric. Therefore, the result is 0, and that's the proof that this quantity within the brackets here is a constant of the motion. So what does it mean? Well, if xi is a time-like Killing vector, if you have a translational symmetry with respect to time, then the conserved quantity is going to be something like an energy. And that we're used to in classical mechanics. If you have a Hamiltonian that doesn't depend on time, you know that the energy of the particle is going to be a constant of the motion. If the Lagrangian of a particle is not explicitly dependent upon time, then there's an energy that happens to be conserved. So it's the same idea here. So if xi was the time-like Killing vector that we have over here, then this inner product here would be interpreted as an energy parameter. If you have a space-like Killing vector, for example, something describing a rotation, well, if it's a space-like translation, it would be the component of the momentum vector in that particular direction. And if it's a rotation, if the Killing symmetry is a rotation, then it would, this quantity would be interpreted as a component of an angular momentum vector. So just this notion of generalized momentum that arises in Lagrangian mechanics is basically manifested here through this quantity right here. It's basically the same thing. So, just going back to the example up here in the static spherically symmetric space-time, U alpha C alpha, when we're talking about the time-like killing vector, would be interpreted as an energy, but I'm putting a minus sign here, and I'm putting a tilde on the energy for two reasons. Here we're talking about the inner product of a time-like vector with another time-like vector. And because of the minus sign in the metric, that's always going to be a negative number. So whenever you're dealing with two future-pointing time-like vectors, their inner product is always going to be negative. So I'm putting a minus sign here just to make sure that the energy is actually positive. And I'm putting a tilde because I'm really talking about the energy per unit mass, because even though I was talking about momentum all along, the construction that I have here is in terms of the velocity vector, not the momentum vector. So I've divided by the mass, basically. So instead of calling it the energy, I call it the energy per unit mass, and I put a tilde on top of it. So it's really energy per unit mass. And then if we're talking about the rotational killing vector, then we would be, so here the inner product would be positive or negative. There is no assigned sign here. Here we would be talking about the angular momentum of the particle per unit mass. All right. So any questions about that? Okay. So I don't think there are big surprises here. I think you've seen things like that before. Something I should warn you about is that when we talk about geodesic motion in various space-times, it's possible that we refer to many different things when we talk about the energy of the particle. And usually that can lead to some confusion because I talk about energy, you talk about energy, and it turns out we're not talking about the same thing at all. So it's very important to distinguish this energy from other notions of energy that might come up in a discussion. So I just want to say a few words about that. Well, I'll just talk about two notions of energy. I think we can probably come up with some more, but I think I'll focus on just those two because those are the two important ones, and it's important not to distinguish them, and not to confuse them. So one notion of energy is the conserved energy that we just talked about. And another way to call it would be, in the case of a space-time that's asymptotically flat, like our Schwarzschild space-time, we could also call it the energy at infinity. So that energy is, as I defined it, the inner product between the time-like killing vector and the velocity of the particle. That's a conserved energy. So therefore, it's a useful quantity. It's, it has every right to be called an energy. But it's a very specific notion of energy that refers to something very specific involving the killing field. The reason why I call it the energy at infinity is because suppose that I start the particle at infinity and I let it move in my space-time, but I go out to infinity to measure its energy. So an example of this is I have a black hole over there, and then I throw a particle, and I throw it at infinity. I throw it at I throw the particle at the black hole starting from infinity, with or without some initial speed. So depending on what I want to do. At infinity, we're dealing with flat space-time, right? Because the space-time is asymptotically flat. At infinity, the for velocity would have exactly the same form as it would have in flat spacetime. So if it's moving radially, for example, there would be a normalization factor, there would be a component along the time direction, there would be a component along the radial direction, and I may as well suppose that for my purposes here, there are no angular components. So gamma would be the normalization factor that guarantees that, so, you know, I'll just call R dot, okay. So gamma is just the usual Lorentz factor that guarantees that my vector is properly normalized to a constant that happens to be equal to 1. So, right. When I calculate this, I find that the energy of the particle then is going to be equal to the time component of the velocity vector. And with the minus sign included, I find that this is just equal to gamma. So that energy is always given by the energy that I gave it at infinity, which is equal to gamma, the usual gamma factor, the energy per unit mass. And it's always equal to the energy that I give the particle in infinity, because this never changes as I follow the motion of the particle. So one way of understanding the meaning of this quantity, I mean, it's not a big deal, but it's important to know what we're talking about. One way to understanding what this is that, well, it's basically the energy that a particle would have at infinity if the particle was ever at infinity and I measured its energy there. Right? The reason why I'm talking about this is that I want to distinguish that from the second notion of energy, which also occurs in a conversation. The other one is the locally measured energy. By an observer in space-time. And that's a different notion of energy. So the idea here is that I have the particle with for velocity u, but now I have an observer that moves with its own, for velocity. So we have an observer that moves with a different velocity vector. The observer could be moving with a particle, but there is no reason to assume that it would. Okay? The locally measured energy, again per unit mass, just to make this consistent, is pretty much by definition, but that's something you can think about and recognize, that it's minus the inner product between those two vectors. That you can justify, or you can verify for yourself, and talk and think of doing this calculation in a local Lorentz frame. I'm going to be talking about local Lorentz frames a little bit later. A local Lorentz frame that's attached to the observer. In that Lorentz frame, the observer would have a for velocity with an entry 1, 0, 0, 0. There's only motion along time in that frame, no motion in space. So that's the co-moving frame of that observer at the time you make the measurement. The energy as measured by that observer is going to be the time component of the velocity of the particle in that frame. And one way of doing the calculation in an arbitrary frame is just to take this inner product here. So the claim is that this is the energy per unit mass that locally an observer would measure for our particle moving in that spacetime. That is not going to be equal to this. Two very different notions of energy. They refer to very different measurements. One is, a measurement that you think you may want to carry at infinity, or you may be able to carry at infinity if the particle was ever there. The particle doesn't have to be there in order to get an energy at infinity. So that notion of energy is a property of the particle, regardless of whether it's, it was ever at infinity. But if you want, if you ever want to measure this, the particle somehow would have to be at infinity. Otherwise, it's something you have to, measure indirectly. You wouldn't be able to measure this directly unless you go out to infinity and measure the energy of the particle there. That is the energy of the particle that anyone can measure wherever the particle happens to be. You just go there, measure the energy of the particle, and that's what you get. And there's no reason for this to ever be equal to that. And in fact, if you measure the particle several times on the, if you locally measure the energy of a particle as it moves around, you will find that the value changes depending on where it is in space-time. So this is not a conserved quantity. This is not conserved where this is conserved. So if we have a conversation and I talk about the energy, you better, be sure, or you better ask me, what kind of energy am I talking about? Am I talking about a locally measured energy, in which case I means this, or am I talking about the energy at infinity, in which case I mean that? And unless we're clear on what we mean, we may have a lot of confusion. And one place where we can have a lot of confusion is because it turns out that it's possible for that guy up here to be negative. This guy will never be negative. So this guy is always positive. Whenever you locally measure the energy of any particle, it always will have a positive energy. But this energy at infinity can be negative. When we talk about the Kerr black hole and we talk about the ergosphere, we're going to see that it's possible to create particles inside the ergosphere that have a zero killing energy, negative killing energy. It is possible to do that. Those particles can never escape to infinity, because if they could escape to infinity, that would mean that I can be at infinity and measure this energy and find a negative value, and that's completely impossible. So those particles can never go to infinity. I can never measure their energy there, and I will never measure their energy to be negative. So what I'm saying is that even in those occasions where we can have a particle with a negative energy at infinity, any local measure of that particle anywhere in space-time where the particle is allowed to be will always be positive. So negative energy particles in GR are possible, but we have to understand the meaning of this. It's really the meaning of this energy that can be negative, but any local measure of energy, even for those particles with negative energy, those locally measured energies will always be positive. It's good to think about this. It's good to keep that in mind because, you'll hear a lot of talk about negative energy particles. You'll hear about that in the context of Hawking radiation. You'll hear about that in the context of various things, the Penrose process around a Kerr black hole. But it always refers to that quantity, which is a conserved quantity. It never refers to this locally measured energy that is accessible to any local observer and will always return a positive value. All right. The discrepancy between this measurement and that measurement, so if you do have a particle that falls from infinity, so you've measured this energy, and then you go deep into space-time and measure its energy again, you will find that the energies don't match. The reason why they don't match is that because of the redshift factor. So as the particle moves in, its energy gets redshifted by the gravitational field, and therefore any local measures of energy will give a different value from the energy you would measure at infinity if you could measure the energy there. All right? So I could say something similar to angular momentum. There's a distinction between the conserved angular momentum and the one you would measure locally. But here the distinction is not, well, it's still an important distinction in the sense that we have to know what we're talking about. But here there's really no, there's really no notion that the angular momentum has to be positive or negative. So, I mean, angular momentum is just going to point in the direction in which the particle is rotating. So if it rotates this way, it's positive. If it rotates the other way, it's negative. So there's no alarm bells that go off when you find this to be negative or positive. Whereas when this turns out to be negative, then you say, well, okay, there's something weird going on. But even though something weird is going on, there's still something you can rely on, and the thing you can rely on is that any local measure of energy will always be positive. All right? Any questions about that? Okay, so let me say, so that's my discussion of killing vectors and their relevance for conserved quantities. I want to say a couple of things that I'll just introduce here just to make sure that you're aware of them, and then I'll move on to curvature. Let's see, where do I want to go? Sure. All right, I just want to talk about the metric determinant. Which I'm sure you've encountered before, but because we're going to be using it a lot in various parts of the course, I just wanted to be sure that we've covered the basic aspects of this. So G, by definition, is the determinant of the matrix you get when you line up all the the elements of the metric tensor in an array. So G is the determinant of this. It's always going to be negative in space-time when you have one negative entry in your metric and then 3 that are positive. So for that reason, we normally talk about minus G instead of G, so we make it positive. And what we really need, though, typically in a calculation is the square root of minus G, the square root coming from, all sorts of different directions. So this is the basic quantity that arises in all sorts of contexts when you do calculations. So one of this is when you do integration. So when you integrate a scalar field over a region of space-time, a 4-dimensional region of space-time, what you find is that the invariant volume element that you have to use is this one. So, so you can do the integral in any coordinate system you want. The only thing that you need to do is to make sure that you incorporate the proper Jacobian in the measure of integration, and the Jacobian actually turns out to be that square root of the metric determinant. So that's a very important place where we encounter the metric determinant. The other place where we encounter it is when we calculate a contracted component of the Christoffel symbols. And if you do that calculation, you find that this is equal to 1 over square root of G times the derivative of the square root of G. And that's something that comes straight out of, understanding the rules of how you differentiate a determinant. So if you change the elements of a matrix, you're going to be changing the determinant. So you can write down a formula that relates the change in the determinant that correspond to the change that you make in the individual components. And when you put it all together, you find that there's a bunch of rules that relate how the metric determinant changes in terms of how the metric components change. And when you put it all together, you find that there's a nice identity here for the contracted Christoffel symbol like that. And in the book, I give you a derivation of that. One consequence of this is that there's a very efficient way of computing the four-dimensional, the covariant divergence of a vector field. So if you calculate the covariant derivative of a vector field, then you can take a contraction. That's what we would mean by the four-dimensional covariant divergence of that vector field. Well, if you do the calculation, you find that this is equal to the partial divergence. But then there's a Christoffel symbol terms that now involves the contraction of those two indices, and you get that, right? So if you plug that in, then you find that this is a alpha comma alpha plus 1 over the square root of g that multiplies the derivative with respect to beta of the square root of g, and then you multiply this by beta, and then you can combine all of this. This is a dummy index, so I can change it into beta, and you can rewrite the whole thing in a very neat form involving only partial derivatives. So that turns out to be handy sometimes when you want to calculate something by hand or calculate something quickly. You don't have to. So when you're instructed to calculate something like this, the covariant divergence of a vector field, you don't need to go ahead and calculate all the components of the Christoffel symbols. You can just take a shortcut, and calculate it this way. And that turns out to be handy for practical calculations. It's also handy for proving various things, and we'll come back to that at some point in the course. Another way where this is useful is when you have the divergence of an antisymmetric tensor field. So for B alpha beta antisymmetric, then the claim is that the covariant divergence of this is also given in terms of a formula very similar to what we had before. And that you can prove. You can basically do the same calculation I did here, except that now you would get an additional Christoffel symbol term, but you would use the antisymmetry of the tensor field to kill that extra term, and now you're back to exactly the same calculation. So it's very important for the tensor field to be antisymmetric. If you were dealing with a tensor field with no symmetries or a tensor field that would be symmetric, then this equation just wouldn't be valid. It wouldn't be true in that case. But if it's antisymmetric, then you have this very neat way of expressing divergence. So I just wanted to mention this because we'll have occasion to see this later on in the course. Another way where the metric determinant occurs is in what's called the Levi-Civita tensor. And that's also something I wanted to introduce because we'll need it later on. So it's Levi-Civita. So that's a tensor. It's a completely antisymmetric tensor, and I call it epsilon. That tensor involves the metric determinant, and it involves something which is not a tensor that I denote in this way, and that is the completely antisymmetric permutation symbol. Now, for those of you who have studied forms, you'll remember that when you integrate over a manifold, you really integrate over a form. So the proper operation of integration over a manifold, as defined in mathematics, is one where you integrate over a form. If you're integrating over a four-dimensional manifold, you're integrating over a four form, which is basically a fully antisymmetric tensor with four indices. This is the volume form in 4D spacetime. I just mentioned this in passing. I won't be emphasizing forms in this course, but this is something that you won't be surprised to see later on will reoccur when we talk about integration. When we do hypersurface integration, we'll see that happening again. And the fundamental reason why it shows up in those contexts is because, well, it's really inherited from the proper form way of doing integration on a manifold. So the 4 form is really where it starts. The volume form in space-time is where it starts. And, with that point of view, you won't be surprised to see that the square root of the determinant would occur here, because, it's really something that tells us something about volume elements in space-time. And therefore, it's not surprising that the volume form in space-time is proportional to the metric determinant. The rest of it is just a way of handling the antisymmetry, the complete antisymmetry of that tensor with respect to any exchange of indices. So it's the permutation symbol. So it does the usual thing, right? So if you have if you have the canonical ordering of the indices, you get 1. If you consider any exchange of indices, for example, 1, 0, 2, 3, you get a -1. If you have any even permutation of the original string, for example, 2, 3, 0, 1, you get a 1. If you have any odd permutation of the original string, for example, 2, 0, 3, 1, you get a -1. And if you have 2 indices that agree, you get 0. So it's the usual thing, right? The completely antisymmetric permutation symbol. And that's something that by itself would not transform as a tensor. But when you combine it with the metric determinant, you form a quantity that does have a tensorial nature, and you have a proof of that in the book. So I just introduce it here just so that when we come back to that in chapter 3 of the book, this will make an appearance, and you'll sort of know where it comes from, and, well, we'll know how to use it. So again, in the book, I have a proof that this is really a proper tensorial quantity. You can prove that this guy over here does transform as a tensor under a coordinate transformation. All right? Okay, let's move on from that, and let's do curvature. So again, I expect that you have encountered the Riemann tensor and its, friends, before in your life. So I'll just give a few things to refresh your memory, and then I'll spend some time talking about geodesic deviation, because I think it's a very pretty thing that tells us a lot about the importance of the Riemann tensor in differential geometry. All right, so curvature tensors. So the way that the curvature enters in differential geometry is when you notice that operations of covariant differentiation don't commute. So it does matter how, in which order you take 2 covariant derivatives when you're acting on a vector or a tensor. So for scalars, in fact, it turns out that covariant derivatives do commute. So if you take a scalar quantity f and you calculate its covariant derivative with, in the order alpha first, beta next, and if you were to consider doing it in the opposite order, beta first, alpha next, you would find that the operations actually commute. And the way to prove this is to just expand out the covariant derivatives. The first terms you'll get are going to be the partial derivatives, and those commute. then you'll end up with a bunch of gamma terms, and you'll find that, well, by virtue of this minus sign over here, you would find that all the gamma terms actually cancel out in this calculation. So for scalars, we have the usual property that two derivatives commute. It doesn't matter in which order you take them. For vectors and tensors, they don't. And that essentially can be used as a way of defining the Riemann tensor. So the way it works, and here you have to do the calculation to show that it really does work like this. If you take a vector, you differentiate it first with respect to alpha and then beta, and then you do it in the opposite order. All of those operations are tensorial, so the right-hand side will be a tensorial thing. The magical thing that occurs is that the right-hand side depends only on A and none of its derivatives. And that's what you get. You get some messy thing, and you get something that involves only A and none of its derivatives. So you might have expected that, after differentiating twice, that after doing this, this combination of things with the minus sign, that there would be all sorts of things left over, like A and its first derivative, maybe even its, well, probably not its second derivative, but at least its first derivative. And the answer turns out not to be so. The answer turns out to be a rather messy thing involving gamma and derivatives, but the right-hand side depends only on A. It's proportional to A. That thing over here is a tensor, and it's called the Riemann tensor. And if you write it in full, I won't do that here, but the Riemann tensor is basically something that can be written in terms of derivatives of gamma plus terms involving gamma squared terms. So it's rather messy, and that's something that, well, you would get as a result of doing this computation in full. So that's what happens if you, take two derivatives of a vector field. You can do something similar for a dual vector. And you would find something, again, similar. In this case, you would get a plus sign. And the way the indices work out in this way, and that's something I never remember. You have a summation index here. You have the mu index over here, alpha, beta. And then you have p nu down here. So if the index is down, you get a plus sign. If the index is up, you get a minus sign. And then the indices sort of arrange themselves this way. And the last two indices are always the indices that correspond to the ones you differentiate with. And then, you can repeat this for tensors. If you have a tensor with two indices, you would get two Riemann terms. And, the sign would depend on, whether the index is up or down. And then if you had a four-index tensor, well, you would have four Riemann terms. And the indices would just arrange themselves in the way that they have to in order to make everything work. Okay, so that defines the Riemann tensor, and that's really the thing that tells us whether we have a genuinely curved manifold or whether we were just dealing all along with a metric presented in a strange coordinate system. So in physics, in GR, it really means that you have a true gravitational field. You really have gravity in your space-time if you have a non-zero Riemann tensor. If you have a complicated metric and it gives you a zero Riemann tensor, that means that you were dealing with flat space-time all along. It's just that the metric was presented in a very strange coordinate system. So the Riemann tensor is really the diagnostic of a curved manifold. If it's non-zero, you have true curvature, you have a true gravitational field in your space-time. So the Riemann tensor is probably the most important, object in GR. It really, physically, fundamentally, it's really the most important object. It really derives from the metric. So in a sense, the metric is really the starting point for everything. But again, whereas the metric is ambiguous, whereas the metric has a dual role of carrying coordinate information plus gravity, the Riemann tensor is a real tensor that is non-zero if and only if you have curvature, if and only if you have a true gravitational field. So the Riemann tensor in GR is really the true carrier of gravitational degrees of freedom, gravitational information. Whereas for the metric, you never really know. You know, it has this dual role. Yep, question?
So can you get the metric from the Riemann tensor?
You cannot. So I don't think there's an algorithm that allows you to calculate the metric from the Riemann tensor because the metric requires extra input. So the metric requires a choice of coordinates. Now, later on, we're going to talk about Riemann normal coordinates, which is a way of constructing a metric from a Riemann tensor and derivatives and extra terms. The point is that you can do it, at least in an approximate sense, in a series expansion sense, by incorporating the Riemann tensor, but making very specific coordinate choices along the way. Right? So the short answer is that, in general, you cannot get a metric, a unique metric from a Riemann tensor. If you give additional input, like a choice of coordinates, you may be able to do it.
But to write down the Riemann tensor, you already have to make a choice of coordinates.
To get to the Riemann tensor from the metric, of course, you take the coordinates that's given to you. But the point is that so in that direction, there's an algorithm that works for any coordinate system. In the other way, there's no algorithm that works for any coordinate system. You would have to provide additional non-algorithmic input into the calculation. Yep.
If we are dealing with a manifold which the metric and connection are not necessarily related, is the Riemann tensor dependent on the metric, or is it dependent on the connection?
Just depends on connection.
Okay.
Yeah. So in a situation in a differential geometry where the connection is independent from the metric, the Riemann tensor ends up being independent from the metric as well. So it's really a construction that comes straight out of the connection. Yeah. Other questions? Okay. So let me just mention the symmetries of the Riemann tensor because they're very important. One that's obvious from the start is that you would have an antisymmetry with respect to exchanging alpha and beta. You can see it on the left-hand side. If you exchange alpha and beta, you pick up a minus sign. So that has to be reflected on the right-hand side. So if you leave the first two indices alone and you exchange the last two indices, you get a minus sign. And that's something that when you do calculations, you always have to remember. I mean, that is the sort of thing that allows you to simplify things very quickly. Whereas if you don't remember any of those symmetry rules, you may end up carrying way more terms in your calculation than you should. The symmetry that's not apparent from those equations, but is there when you actually write out the Riemann tensor in full, is that it's also antisymmetric under an exchange of the first two indices. Again, very important to remember that. And another symmetry that's also there but not obvious is that what you can do is to exchange the first pair of indices and the last pair of indices, and also get, and this time you get a plus sign. You get exactly the same thing. And there's another one. There's a cyclical identity that says that if you cycle through the last three indices, the result adds up to 0.
The third line, you don't seem to have any change between the indices.
Sorry,
Alpha,
which
beta.
one? Oh, sorry. Yes. Right. So the first three ones are very essential. The last one, sometimes it's good to remember, but you would be doing a lot more work than you should if you didn't remember to take into account the first set of symmetries. The last one sometimes is important, but not as frequently as for the first three sets. When you put it all together, what that means is that while even though we're talking about a large object with 4 indices, And if it then, if the Riemann tensor didn't have any symmetries, the number of independent components in the Riemann tensor would be 4 times 4 times 4 times 4. That's a large number, but all those symmetries, in fact, reduce it down to something much smaller than that. And there's a counting you can do that would be valid in arbitrary dimensions, but in 4D, what is found is that, well, the Riemann tensor actually has 20 independent components. As a result of the symmetries, and that means that it's actually, a manageable object, so it doesn't carry an awful lot of, the number of degrees of freedom is still restricted. If you're in 2 dimensions, you have 1 independent component. So calculating a Riemann tensor for a 2-dimensional surface is very easy. You just have 1 calculation to make. When you calculate a Riemann tensor for any random spacetime, say Schwarzschild, the problem that arises if you do it by hand is that you end up calculating all sorts of terms that end up to be zero in the end. So there are all a bunch of components of the Riemann tensor that happen to vanish, and if you don't know that ahead of time, well, you can do a lot of work just to calculate the 0 ones, and instead of focusing your effort on the ones that are not 0. In the old days, when I was growing up and learning, differential geometry, that was a big deal because there were no machines that allowed you to do these calculations, so you had to do them by hand, and there were fancy techniques that you can learn based on forms that allowed you to do that efficiently. These days, of course, we all rely on computers, so, well, that's something I should tell you. So when I give you homework assignments, I do expect you to have some familiarity with some package. My favorite one is Maple with GR-Tensor. So GR-Tensor is a tensorial package you can download for free, install it under Maple, and that allows you to input a metric and calculate anything you want to know from it, including the Riemann tensor. You can define your own vectors, you can define your own quantities, let it calculate it for you. So all those routine operations that would have required pages and pages of effort in the old days now just require pressing enter on your computer, and you get your answer within a fraction of a second. It's almost too easy. I mean, the good days were hard. We had to walk miles in the snow to go to school and all that. But now it's much easier. So my recommendation to you is that before you attempt to do the problems that I will be assigning you, there's going to be some that are there's going to be some that, there would be no payoff in doing it on the computer, but there's some problems that require a lot of routine calculations that you should, learn how to do it on the computer. The learning curve might be steep at first, but you're going to thank me in the end. You're going to save yourself a lot of time if you do that. So my favorite is Maple and GR-Tensor. There's an intrinsic tensor package under Maple that you can use if you prefer it. If you use Mathematica, there's a GR-Tensor package and others. So there's a multitude of choices, for what you want to use. But my point is, pick one, learn how to use it, and it's going to be useful for a lot of what you do. Okay, so here's the Riemann tensor, 20 independent components. What we tend to do with the Riemann tensor is to boil it down to simpler things. So one thing we can do is to take a contraction of the Riemann tensor under the third and first indices and get something smaller, which is known as the Ricci tensor. Now, when we take contractions of the Riemann tensor, of course, we have to do it right, because if you contract on the first and second indices, the antisymmetry will tell you that the result has to be 0. If you were to contract on the third and fourth indices, same story. So basically, the only possibility modulo symmetries is to contract over the first and third indices, and that gives rise to a symmetric tensor. And it has 10 independent components. So from the original 20, we got rid of 10, and there are 10 remaining components. The other 10 are contained in what's known as the Weyl tensor. I won't write it down here, but in one of the problems in chapter 1, I actually defined the Weyl tensor. And you can think of the Riemann tensor as being split into two tensors, one being Ricci with 10 components, the other one with Weyl, which is the remaining 10 components. The Ricci tensor is basically the trace part of the Riemann tensor. The Weyl tensor, in a sense, is the trace-free part of the Riemann tensor. So you can split it up nicely like this, and for some purposes, it's useful to do that. We have a Ricci tensor. We also have a Ricci scalar, which is what you get when you take the contraction of the Ricci tensor with itself, with its two indices, and that's obviously a scalar, so it has only one component. So by doing those contractions, we go from full description involving all the degrees of freedom that the curvature has down to something smaller and something smaller still. So we go from full to cruder. And, you know, there is curvature information contained in the Ricci scalar, but it's very limited. If you want the full curvature information, you have to consider all the components of the Riemann tensor. That's where all the information is. The reason why we do this mostly is because at some point we want to write down the Einstein field equations. And the left-hand side of the field equations is going to be some packaging of these things. So the Einstein tensor is a linear combination of the Ricci scalar and the Ricci tensor. And the reason why it was this combination that in the end was adopted as the left-hand side of the field equations is because as a consequence of the, I should backtrack. There's an additional set of identities satisfied by the Riemann tensor that concern its covariant derivative. So there's a set of Bianchi identities. There's a Bianchi identity that, that is also satisfied by the Riemann tensor, and it's something involving its covariant derivative. There's a contraction of the Bianchi identities that ends up being a property of the Einstein tensor, and that property is that the covariant divergence of the Riemann of the Einstein tensor happens to vanish. And that turns out to be a very important property of the Einstein tensor that singles it out as a very plausible left-hand side for the field equations. Now, you know the story that Einstein really struggled many years to eventually arrive at the final form of GR, and that struggle, he had to go through. But that struggle, he had to struggle so hard because he didn't know about this. That's not something he knew about. Mathematics was not there yet. So he didn't know about the Bianchi identities. He didn't know that this was, the right ingredient for the right-hand side. So for a very long time, he tried to make the Ricci tensor itself the left-hand side of the field equations, and that never quite worked. And it's only when he, came to understand all of this in a very dramatic turn of events, in November 1915, that he came to understand that that the right-hand side of the field equations had to be the Einstein tensor. So the Einstein tensor, like the Ricci tensor, also has 10 components. And finally, when we have all of this, then we have the Einstein field equations, which tell us that, well, the right-hand side of the field equations is the Einstein tensor, and the right-hand side, if you put in all the constants, is this proportional to the energy-momentum tensor. The energy-momentum tensor incorporating all the matter information. That's, the part of the field equations that tell us where the matter is and what it's doing. It's, the energy-momentum tensor is basically something involving the mass density, the currents, the pressure in your matter, and all of this. So that's all on the right-hand side. And on the left-hand side, we have the Einstein tensor. So that's the curvature part. That's the matter part. And then this property, this purely geometrical property of the Einstein tensor, plus the field equations tell us that the divergence of the energy-momentum tensor has to be 0, which is something you can think of as a statement of energy-momentum conservation in curved spacetime. So that's the energy-momentum tensor. Which describes the matter, And that's the statement that the divergence of the energy momentum tensor has to vanish, and which is really a way of stating energy momentum conservation in your spacetime. So in GR, we have this interesting relationship between curvature and matter. And in fact, I think for Einstein and for many people, there's a temptation to look at this and to say that energy momentum conservation is really a consequence of geometry and the Einstein field equations. So if you subscribe to the view that gravity is about geometry and you adopt the Einstein tensor as the left-hand side of your field equations, well, then, this is a purely geometrical identity. There's no leeway about this. This is, just an identity. It's called the Bianchi identity. So that comes straight out of the geometry. If you impose the Einstein field equations that relate the geometry to the matter content, then as a consequence of this and the Bianchi identity, you're driven to a statement of energy momentum conservation. So a logical chain here would be to say that first comes geometry, then comes the field equations, and as a consequence, we have the matter satisfying energy momentum conservation. So one of our most cherished beliefs and feature of all of physics, conservation statements, energy, angular momentum, momentum, and so on, are all contained here. And in this view, it comes from geometry and the Einstein field equations. Well, that's one view, right? You can subscribe to it. You don't have to if you don't want to. Another view would be to say that, well, this is really much more fundamental. Energy momentum conservation is something that you should have regardless of what the field equations are. So what we came to understand, of course, in the course of the last century or so is that, well, the Einstein field equations are certainly very appealing. They're very simple. It's probably the simplest theory you can write down that involves a metric for gravity. It's the simplest theory that has a geometrical origin for gravity. But there are lots of ways you can modify the field equations. And people have played this game a lot in the last 100 years. They've come up with all sorts of alternative theories, and the game continues. I mean, every day, every week, there's a new theory on the archive that's either a modification of GR or some new theory. So to expect that this is going to be the end, the last word on gravity is probably a bit naive, even though it's been surprisingly and remarkably successful. There's probably going to be a day in the future somewhere, maybe now, maybe later, maybe 10 years ago, but I still think it's in the future, where we're going to have to seriously consider modifying the field equations of GR to account for measured phenomena and various other things. So the strict relationship between this and that is really mediated by a very specific set of field equations. If you were to modify the field equations, presumably you would invent a theory that would still respect this, right? You would still have your, matter in the universe satisfying energy momentum conservation. Well, you might be crazy. I mean, this is PI, so anything goes, right? So you might still be crazy, but let's assume that your theory would still respect energy conservation. So you still want that. You still will have that, of course. That's just an identity. But you may not have that. And therefore, this will no longer come as a consequence of that if the field equations end up being more complicated. So the view I prefer is the view that says that, well, this is really something very fundamental. In fact, it's really a consequence of a deep symmetry of physics. It's really a consequence of, general covariance and all of these things. So there's really something very deep about this that's not at all or not necessarily connected to the field equations. So I would want that in my physics, even though someday I may accept that this is not true anymore. But this, I would want that to be true always, at all times, forever. But in GR, you can certainly, so if we adopt those field equations, and we will in this course, we could add a cosmological constant, but that won't change the story. In GR, you can certainly see this in that as being very tightly connected things. So energy conservation and the Bianchi identities are very tightly connected to each other. Anyway, I just wanted to give you a little bit of an editorial comment on all of that. Okay, so in GR, so we have the Riemann tensor that tells us whether or not we have gravity, and then we have, the cruder versions of the Riemann tensor that tells us what the left-hand side of the field equations are. We have the matter distribution on the right-hand side, and then, in principle, it's just a matter of solving that to find solutions and deal with physics in curved space-time. A bit of a miracle here is that, well, at first, nobody expected that you could find solutions to this except for Schwarzschild. So Schwarzschild came along, within days of, the theory being published, and he was able to find, the first exact solution to the field equation. So that was already a miracle. And then for decades, nothing happened in terms of finding exact solutions. And then in the 60s, there was an explosion. And now there's a big, thick book, that tells you, that lists and catalogs all the known exact solutions to Einstein field equations. And if you take that thick book and you ask how many of those are physically relevant, it goes down to a page. And we're back to Schwarzschild, Kerr, FRW, and that's basically it. I mean, you have a few more exact solutions that are, relevant, but even though there's a multitude of exact solutions, most of them turn out to be not very relevant. These days, of course, the explosion has started again because people are doing that now in higher dimensions. So as you open up the number of dimensions, the number of exact solutions has also mushroomed and multiplied greatly. I think it remains to be seen how much of that will turn out to be physically relevant when, our kids and grandkids are looking back on this. They might, they can judge, they will be able to judge that. But in any case, the point is that it's very hard to find physically relevant exact solutions to the field equations, and more time than not, you end up trying to find approximate solutions because they have more relevance to what you want to do. So something to think about, and then I'll break, is that suppose you wanted to describe a space-time that has two bodies in it. Two orbiting bodies, something very simple, something that we see everywhere around in the universe. Well, when you find an exact solution to the Einstein field equations, you have to find a complete spacetime, right? It's not just good enough to describe the motion for a few orbits. You have to describe the motion at all times. That's what it means to construct a spacetime. You go all the way to minus infinity. You go all the way up to the infinite future. So now your two bodies, well, they weren't always orbiting. So at some point, the bodies had, were sort of diffuse nebula that at some point, suppose we're talking about a binary star. Well, the stars have a past, right? They didn't always exist as a star. So in principle, your solution would have to start from a diffuse nebula. It would have to describe gravitational collapse into two individual stars. It would have to describe the orbital motion. A feature of the orbital motion is that it emits gravitational waves, so you have to incorporate that. As the system keeps on evolving, emitting gravitational waves, the orbits start to shrink. They keep on shrinking for millions and billions of years sometimes. At some point, the stars merge. Maybe one of those stars will eventually form a black hole. Maybe the other one will form a neutron star. All of that has to go into the solution. And eventually, you have the merger, and eventually things quiet down, and eventually, for the infinite future, you have a single black hole that has settled down to its final state. All of that would have to be part of an exact solution to the Einstein field equations, describing a simple thing like two orbiting bodies. No one was able to write this down, right? So it doesn't exist. So what you can do is to formulate approximations that try to capture some of that. You can chunk up your space-time so that you only capture a finite time instead of the infinite time. You can do parts of it. You can do the final black hole really well. You can do the orbiting very well, the orbiting bodies very well. If the orbiting speeds are slow, if the mutual gravity is weak, you can do post-Newtonian theory. So bottom line is that typically we don't focus so much, if we want to do interesting physics, we don't focus so much on exact solutions. We just try to come up with good approximate solutions to the Einstein field equations. So you had a question?
Well, the Einstein equations only have 10 components, but the Riemann tensor has 20.
Yeah.
So do you really need 20 components to describe all the physics?
Yeah, so to describe all aspects of the gravitational field, you need the 20 components. But what you're asking is that how is it possible to get 20 components out if you only have 10 equations to deal with? And again, there's something a little bit funny going on, because even though you have 10 equations, what you're really trying to get to are the 10 components of the metric from which you can derive everything. But in order to do that, again, you have to specify coordinate conditions. So not all of those equations are independent because of the Bianchi identities. There's some redundancy in those equations. But when you factor in the coordinate conditions, so that when you factor in the fact that the metric can be defined only up to coordinate transformations or diffeomorphisms, the way it's normally said, then you find that you have enough information in the field equations to get the metric modulo diffeomorphisms. And if you have the metric, then you have enough information to calculate everything about the Riemann tensor. So it all works out. Yeah.
So you're saying the other components are fixed by diffeomorphism invariance?
Sorry, what?
You're saying that the other components are fixed via diffeomorphism invariance?
What I'm saying is that the field equations will allow you to get 6 of the 10 components of the metric, and the remaining 4 will basically represent the coordinate information that a metric also has to carry. But when you actually calculate the Riemann tensor, those 4 coordinate pieces are irrelevant. So the 6 pieces that are really fundamental to the metric are what so out of the 6, you'll get the 40. You'll get the 20. So you still get something that's derivable from something simpler. But the Riemann tensor is really, the full amount of information. It's just that you can derive it from a simpler set of quantities. So I'm not expressing this very clearly, but there's an algorithm that allows you to take the 6 important components of the metric, the gravity component of metrics, to calculate the 20 independent components of the Riemann tensor.
So by independent components now, what we're just saying is that by the symmetries alone, all the components go to 20 components, but they're not free parameters.
No, okay, no, thank you for clarifying this. Here I was just talking about the algebraic independence. So we have 20 algebraic independent components. But that doesn't mean that we have 20 degrees of freedom. In fact, if we were to count the degrees of freedom, we would have to do a very careful calculation. But the point is that those 20 components can be derived from what I claim are the 6 essential pieces of the metric. They all follow from that. And those would be the essential degrees of freedom in a metric. It gets a bit more complicated than that, because you would want to distinguish the degrees of freedom in the metric that can be directly related to matter and those that are purely independent degrees of freedom. So like in E&M, you have pieces of the electromagnetic field that relate directly to the current and charge densities. And then you have truly independent degrees of freedom to the electromagnetic field, which are the radiative degrees of freedom. Well, in GR, it's a similar situation. So out of the 6, you still have 4 basically that relate directly to matter, and you have 2 that are truly independent degrees of freedom, and those are the radiative degrees of freedom. Okay. All right, let's break for now, and we'll pick this up again in the afternoon.